Hi everybody. So in this video we're going to just continue really with a gentle introduction to general relativity. And so in this video, still not very much heavy maths, okay, so still not really into the tensors yet. I'm just trying to finish connecting the dots with special relativity and what gravity has got to do with frames of reference. Okay, so how if we take special relativity and we try to free it up into non-inertial frames, how that leads to a discussion about gravity. So I'm going to start by kind of posing a question. Okay, so in normal times when I'm doing this class in a lecture theatre, I always kind of open this question to the floor. Can't do that here, but think for a second about mass. Okay, so mass, a word that we've known for years since we were learning physics at school. We know it appears in Newton's second law and so on, but what is it exactly? Okay, so what does the word mass mean exactly? And probably the way you thought about it at school, which is right, is that mass is a measure of how much stuff there is in an object. Okay, so how much material, how much matter is there. Another way of thinking about mass, and the way we're going to think about here, is it's a measure of how unresponsive an object is to an applied force. Okay, so what do I mean by that? Okay, a measure of how unresponsive something is. Well, think about Newton's second law, okay, which I've written here, A equals F over mi. Now that seems like an unusual way to write Newton's second law. Normally we just write it as F equals ma, but I'm just writing it backwards here, so I'm just writing acceleration is equal to force divided by mass. And why have I put a subscript I on the mass? This I stands for inertial, okay, inertial. So this mi is called the inertial mass. And the word inertia, it means unresponsiveness or laziness. Okay, so why are we saying that? Well, it's because if you look at Newton's second law as it's written here, if you imagine I have, just some object, okay, say it's a book sitting on a table, and I try to push or pull the book along the table. So let's suppose I apply a force to the book, so say it's just a 5 Newton force. The acceleration that I get depends on the mass. Okay, so if it's a book with a small mass, then that 5 Newton force will move the book quite easily, so you'll get quite a large acceleration. On the other hand, if I apply that same 5 Newton force to a different book that has a bigger mass, then the acceleration I get will be smaller. Okay, so that's why I've written Newton's second law this way. Imagine I have some objects, or some different objects with different masses. I can apply the same force, F, okay, so that same 5 Newton force, to all of those objects, but I will get a different acceleration in each. Okay, so the bigger the mass is, the less acceleration I get. Okay, so really, the force F is something that I, as the physicist, can choose. Okay, so I decide to apply whatever force I want, and then nature uses the second law to determine the acceleration using the inertial mass above. Okay, so that's why I've written Newton's second law this way around, because really this is the way that nature thinks about it. So I, the physicist, I apply the force, and then nature determines the acceleration. So this mass, the bigger the mass is, the less acceleration you get. So in other words, the bigger the mass, the more unresponsive your object will be to the force. So that's why we call it inertial mass. So M subscript I. So let's look at a slightly more fundamental example now, rather than a book being pushed along a table. Let's think a little bit about the electrostatic force. Okay, now if you haven't ever studied electromagnetic theory, don't worry, you don't need to know too much here. You will have studied it actually, now that I think about it, earlier in the course. with Dermot. But anyway, we just need the very basics here. So at the top there I've written that the force experienced by a charge Q at a position R in an electric field E is given by F equals Q times E. Okay, so just imagine you have some electric field, doesn't matter where it comes from, you just have an electric field. How is that related to the force that a charge will experience? Well, the force is just the charge Q times the electric field. Okay, and I show then on the next line, as a particular example, if you have an electric field being generated by just a point charge, capital Q, at position RQ, that's how the force would be given there. So F is equal to little q. Okay, so little q is the charge that is experiencing the force. So you've got little q times big Q, which is the charge generating the electric field, times vector r minus rq divided by the magnitude of vector r minus rq cubed. Okay, but at any rate, here's the point, and it's the third bullet point. The force that is applied doesn't depend on the mass of the charged particle. Okay, so look, for example, again at the second bullet point. That's the force for a field generated by a charge capital Q. Okay, so look at that equation on the second bullet point. There's nothing about mass there. Okay, so the electrostatic force, it doesn't care anything about the masses of the particles involved. Okay, so the force F doesn't depend on the mass. It's the acceleration that ultimately depends on the mass. Okay, so that's what I mentioned in the third bullet point. So it's like the electric field is just the fundamental property that's generated by the charge capital Q. You put another charge, little q, in that field, it experiences a certain force that's determined just by the electric field. The force itself doesn't depend on the mass, but the acceleration that it experiences will depend on the mass, okay, through Newton's second law. So that's that third and final bullet point there. So the acceleration will be the force divided by the inertial mass, and the force will just be the charge Q times the electric field, okay, just as we have here, but then divided by that inertial mass. So that emphasizes again the idea that I had in the previous slide, okay, that the force doesn't depend on mass, it's the acceleration that depends on the mass. Okay, so gravity though is a force that behaves a little bit differently for some reason. Okay, so there is a bit of a mystery about gravity, and there always actually has been, and it's that gravity, the force that it puts on a particle, it does seem to depend on the mass of the particle. Okay, so this equation here looks very much like the equation I had in the previous slide for an electric field. Okay, so for hundreds of years we had a theory of gravity, thanks to Isaac Newton, and it said that if you have some gravitational field, little g, then the force experienced by a particle in that gravitational field will be the mass of the particle, little m, times the gravitational field. So for example, this is how the force will look if your gravitational field is just produced by some other point mass at position Rm. So here you can see this force does depend on the mass of the particle experiencing the force. So for some reason, it seems like gravity is a force that's slightly different from other forces in that it does depend on the mass. Okay, and not only that, it depends on the mass in such a way that any particle in the same gravitational field will have the same acceleration, regardless of its mass. Okay, so it's almost like gravity works completely backwards from other forces. Okay, so other forces, so go back to my example of the book, I can apply the same 5 Newton force to different books with different masses, and I will get different accelerations. Go to an electric field, I can put various different electric charges, and let's suppose they all actually have the same charge, and I put them in the same electric field, they experience the same force, but if they have different masses, then they will have different accelerations. But gravity, I put a bunch of different particles in the same gravitational field, doesn't matter what their masses are, I always get the same acceleration. Okay, so gravity is kind of backwards. Okay, and you know this very well. Okay, if I take two objects, if I take a book, and I also take, let's say a car, and I drop them from 100 feet in the air, they'll both hit the ground at the same time, right? Even though the car has a much bigger mass, they both fall with the same acceleration, okay, neglecting the air resistance and so on. So gravity is a bit of a funny force, okay, and really, to be clear, if I just go back one slide, fundamentally, in this definition of gravitational force and gravitational field, this mass m that appears, notice that I haven't put a subscript I on it, okay? And the reason for that is that this m, yes, it's called mass as well, but fundamentally, it is a different quantity. Okay, so the mass that appears in Newton's second law, that's the inertial mass. But the mass that appears in the definition of gravitational field, that's what we could call gravitational mass. It is different in principle. So while the inertial mass is a measure of laziness, so unresponsiveness to an applied force, the gravitational mass is a measure of responsiveness to a particular force, the force of gravity. And so here, actually, from now on, or for the time being at least, I will call the gravitational mass m subscript g. Okay, so here's Newton's second law, first of all. So the acceleration is the force divided by the inertial mass. But then, for gravity in particular, the force is the gravitational mass of the particle times the gravitational field that it's moving in. And so if you combine these two equations, you get this expression for the acceleration of a particle in terms of the gravitational field. So the acceleration will be the gravitational mass divided by the inertial mass times the gravitational field. So that's what we get from fundamental theory, but our experience tells us, as I've just mentioned about the car and the book, that all objects have the same acceleration if you put them in the same gravitational field. In other words, mg over mi is a constant. And in fact, by a choice of units, you can make them equal. So it's an empirical observation that all objects move in a gravitational field with the same acceleration, which by a choice of units is just the gravitational field. In other words, the gravitational mass and the inertial mass, even though they come from two completely different concepts, okay, they are the same. So the inertial mass comes from Newton's second law, gravitational mass comes from the definition of a particular force, gravity, but they're the same. But this is totally empirical. Okay, what do I mean? I mean you can't prove this. There's no fundamental reason why this should be the case. It's just an empirical observation that all objects move in a gravitational field with the same acceleration. It's just something we know from observation. And for a long time, so from Newton right up until Einstein in the 20th century, there was no explanation for this. Okay, no explanation at all. And in fact, people even did experiments where they tested this, so they were able to measure like if there is any difference at all between gravitational mass and inertial mass. So they did experiments on this and they found, as far as they could tell, no, absolutely no difference. So there was no explanation for that until Einstein came along. And the explanation is what becomes the theory of general relativity. Okay, so to get to that, I need to take you back a little bit to something called fictitious forces. Okay, so if you studied classical mechanics last year, then you may have seen this concept of fictitious forces. But if not, I'm going to explain it to you now. So imagine the following setup. So imagine I'm standing outside and I have a bucket with some water in it. So here it is here. And I spin the bucket round in a circle. Okay, so I just spin round and round, and as you know very well from experience, the water will actually stay in the bucket. Okay, so the rope will stay taut, and the water stays in the bucket. Okay, so it's an example of circular motion. Now let's think about the forces that there are on the bucket. Okay, so in our classical mechanics, we know first of all there's the weight that acts down the way. So the weight is just the gravitational mass, so let's call it the gravitational mass, mg, times the acceleration due to gravity, which near the surface of the Earth, that's just uniform. So that's just like G equals 9.81 meters per second squared. So that's the weight down the way. And then we also have the tension in the rope, okay, which will have two components, okay, because the rope can't be totally horizontal. If it were, then gravity would want to pull it down a little bit again. So there are two components. So there's a horizontal component of the tension, which points in the way, and then there's a vertical component which goes up the way. So if we're assuming that the bucket just stays at the same height, then TV will exactly match or equal to mg times g. Okay, so this upward force from the tension will match the downward force. And then we have this resultant force, which is the horizontal component of the tension. It's a resultant force towards the center, and that's what gives you your centripetal force. Okay, so this component of the tension pointing horizontally inwards will be mr omega squared, okay, where omega is the angular speed with which the bucket rotates. Okay, so again, that's a formula that you would know from A level, r here being the radius of the circle. But this m, this is the inertial mass. Okay, so this formula comes from Newton's second law, in fact. Okay, so this one's got nothing to do with gravity. So this is the inertial mass. Okay, now, that's fine. What we're going to think about now is what happens if we change our frame of reference. Okay, so if I am in the frame of reference where I am just somebody else, so an external observer watching this happen, so watching this person spin the bucket round and round and round in a circle, if I am an external observer, then I will see exactly what I've drawn here. Okay, so these are the forces and so on I would see. Yeah, weight down the way, tension up the way, tension towards the center of the rope, which gives you centripetal force, which keeps the bucket in circular motion. Fine, no problem at all. But if I change now my frame of reference, change to where I am the person spinning the bucket. Okay, so, and imagine that as I spin the bucket, all the time I keep my eyes looking down the rope at the bucket. Okay, so I'm in the frame of reference where it's me spinning the bucket and I am looking down the rope at the bucket as it rotates. Now, in my frame of reference, the bucket actually isn't rotating. Okay, in my frame of reference then, it's actually the entire rest of the universe that's rotating around me the opposite way. Okay, think about it. In my frame of reference, if I just look down this rope, the bucket's not spinning, I'm not spinning, it's the rest of the universe that spins around me. And so then I have a problem, because it looks like I have a problem with the forces. Okay, yeah, I've got weight down the way, and then the upward component of the tension, those are fine, but it looks like to me I have this resultant force along the rope, okay, or along horizontally towards me. So why then, in my frame of reference, doesn't the bucket just fly in along the rope? If there's this force pulling it in, why doesn't the bucket just fly in? Okay, in my frame of reference, the bucket isn't executing circular motion. It looks like it's just hovering there in my frame of reference. How can that be? Even though there's a resultant force, why doesn't the bucket just accelerate in? Because the answer is, I am in a non-inertial frame of reference. Non-inertial. So Newton's laws don't apply anymore. Okay, my frame of reference is non-inertial because my frame of reference is accelerating. Okay, my entire frame of reference is rotating. Okay, so my entire frame of reference rotates with the bucket and the rope, and that is why it looks to me like Newton's laws aren't holding. Now, mathematically, dealing with non-inertial frames can sort of be got around by introducing fictitious forces. Okay, so this is where it comes in. So even though I am in a non-inertial frame and Newton's laws don't hold with the mechanical forces, I can introduce what are called fictitious forces to make Newton's laws hold there if I wish to. So what I can do is introduce a fictitious force which doesn't have a mechanical origin, it's just a mathematical quantity, but it points equal and opposite out the way to that centripetal force, and that cancels it out. So in my frame of reference, I can introduce that force, and then Newton's laws do apply. So the bucket now does not accelerate in my frame of reference. So it's called a fictitious force. So they're introduced to make Newton's laws hold in non-inertial, i.e. accelerating reference frames. But here's the key point. Fictitious forces are always proportional to the inertial mass. Okay, fictitious forces are always proportional to the inertial mass. Okay, I don't want to get too much into all the ins and outs of why that is. Okay, have a look in the lecture notes where I try to give an explanation. It's because really you introduce the fictitious force to cancel out an acceleration. Okay, so this force on its own should produce an acceleration this way. I introduce a fictitious acceleration the opposite way. And then the fictitious force is just the inertial mass times the fictitious acceleration. So that's why, basically. But the point is, they are always proportional to the inertial mass. Now, let's think about a different example and see where this becomes useful in getting into gravity. Think about a ball that's just falling. Okay, so just imagine a free-falling ball or a free-falling object. And imagine it in two different frames of reference. So on the one hand, imagine it in a frame of reference where I am just standing on the surface of the Earth, okay, and I just watch the ball fall. So I call it the Earth frame. What forces do I see? Well, I just see a single force on the ball. I just see the force of gravity pulling it down, okay? And that force is the gravitational mass times the acceleration due to gravity. And that is an inertial frame, okay? So as I just stand on the Earth, I am not accelerating. Okay, so my frame of reference is inertial. It's the ball that accelerates as it falls. But then if I transform to the frame of reference where I fall with the ball, if you like, then I am now in a non-inertial frame. So if I am in the frame of reference where I am falling with the ball, then to me, it looks like the ball is stationary. Okay, it looks like it's the Earth that's rushing up towards me. Okay, so this is a non-inertial reference frame. Okay, so actually I am accelerating with the ball, but the force of gravity is still there. Okay, so it's a mechanical force, it doesn't just disappear. So how can I make Newton's laws apply in that frame, that non-inertial frame? I can introduce a fictitious force pointing up the way. Okay, equal and opposite to the mechanical gravitational force. So that's how Newton would describe those two frames of reference. Okay, you've got a falling ball and you can just watch it fall while you're standing on the Earth, or you can fall with it. And that's Newton's description. Okay, and this is how, in fact, you know whether you're in an inertial frame or a non-inertial frame. Okay, the inertial frame doesn't need any fictitious forces. The non-inertial frame always does, okay, to make Newton's laws hold. That's how you can tell which type of frame you're in. But this next bit was Einstein's absolute stroke of genius. He said, look at this problem. There's actually a simpler way to think about it. Okay? And it's like this. So in the Earth frame, well, let me go back one slide. In the Earth frame, okay, if you imagine this falling ball, or in fact, if you go to the ball frame, right, imagine you're falling with the ball, or even just imagine that you are the ball, okay? Yes, supposedly then there is the force of gravity acting down on you, and there's this fictitious force acting up the way. But here's the question. If you are falling, could you actually feel either of those forces? Could you actually feel anything? No, you don't, okay? So if you're in free fall, you actually feel like you're weightless. Okay, so this is actually how, you know, astronauts, like on the space shuttle or on the International Space Station, you know, people think they're floating around in there because they're so far away from the Earth, there's no gravity anymore. That's actually not the case. Okay, the strength of the gravitational field up there is still something like 90% of what it is on the surface of the Earth. It's because they're in free fall that they appear to be weightless. And so there's actually, because you can't feel either of those two forces, Einstein said there's a simpler way to think about this whole problem. Okay, if you can't actually detect either of those two forces, then maybe neither of them are really there. So Einstein said, in the frame where you fall with the ball, or where you are the ball, you feel weightless, not because gravity's pulling you down and there's a fictitious force back up the way, but rather you feel weightless because there are no forces at all. And if you go back then to the frame where you're standing on the earth, the reason that the ball looks like it's falling is because there is a single fictitious force that looks like it's pulling it down. And it's the force of gravity. Okay, so gravitational mass times acceleration due to gravity. And this was an absolute stroke of genius by Einstein. So what he was saying is, actually, in Newton's theory, you've got inertial and non-inertial the wrong way around. It's actually the frame where you're free falling that is inertial. In that frame, there are no forces. And in the frame where you're not free falling, but you're just standing on the earth, that's the non-inertial frame. And the force that we call gravity, that appears to pull the ball to the earth, that's actually a fictitious force. And that's why it's always proportional to mass. Okay? So here, yes, we know by construction, by definition of gravitational field, that it's proportional to gravitational mass, but that's why it's proportional to the inertial mass too, because it's not a real force, it's fictitious. And like all fictitious forces, it must be proportional to the inertial mass. So what we're saying is that gravity is a fictitious force, and by transforming to a free-falling reference frame, okay, so like here, where we transform from the earth frame to the ball frame, okay, a free-falling reference frame, you can actually make the gravitational force disappear completely. So it doesn't have a mechanical origin, it's just a fictitious force. So a uniform gravitational field, at least, like we have near the surface of the earth, okay, where we just assume that the strength of the field is the same everywhere, it can actually be made to disappear by a choice of reference frame. And that's what gravity has got to do with reference frames. Okay, so gravity is apparently a force in Newton's theory, but you can actually just make it disappear by a change of reference frame. Now, this video has become a little bit longer than I thought, so what I'm going to do in the next video is just continue this discussion a little bit with how this applies to the creation of gravitational fields, and also then how this applies to like real gravitational fields that aren't necessarily uniform. So I'll see you in the next video.